Okay, so today I'm going to talk about our project CharmROS, which is empowering PDES with an adaptive runtime system. It's a collaboration between myself, Nick Hill, and Professor Kale here at UIUC, along with Elsa and Professor Carruthers at RPI, and Peter Barnes and David Jefferson at Lawrence Livermore. So first I'll give a brief introduction on DES and PDES. So DES is discrete event simulation. It's a type of computer simulation where the work is driven by the availability of events and the virtual times at which those events occur, rather than, for example, in a time step situation where you have a fixed time increment that you do work at. And discrete event simulations are mainly composed of two key entities, logical processes and events. So LPs are what actually execute events. They make up the state of whatever system you are simulating, and as these LPs execute events, they update their state and move forward in time. These events have virtual timestamps, and therefore, in order to correctly run your simulation, you have to execute these events in timestamp order on the LPs they're intended for. When we're doing discrete event simulation, there's a couple of different ways we can actually run the simulations, the first of which obviously being sequential. However, once we want to move into the parallel domain, we have two basic modes of operation, conservative and optimistic simulations. The difference between the two mainly consists of how we decide which events we're allowed to execute and how to enforce an ordering. But today I'm mostly going to be focusing on optimistic simulations. So for optimistic simulations in PDES, events are executed speculatively. So each processor keeps its own queue of events in ordered timestamp order and executes those events sort of at will, not regarding what events might come in later or what events are being executed on other processors. And then because of this, because we're executing events speculatively, we need to make sure we know how to handle causality errors. So a causality error occurs when an LP has advanced to some particular timestamp and all of a sudden it receives an event from its past. And because we need to deal with these causality errors, we choose to deal with them by rolling back. So what essentially happens when we detect a causality error for a particular LP, we roll that LP to a point back in its past right before it would have received the causality error, and then re-execute events in the proper order. Because we will need to be re-executing events, we need to store a history of the events that we've already executed so that when we roll back, we can re-execute them correctly. And because these simulations generally involve billions or trillions of events, we can't just store everything. We need to be able to reclaim our event memory. And we do this by synchronizing and calculating what's called the GVT. So the GVT is the global virtual time. It's one of the key processes involved in both optimistic and conservative simulations. Essentially, it involves finding the smallest timestamp in the entire system. So essentially, what is the earliest event that we are aware of? Because we need to take every event into account, we need to wait for all of the events to arrive at their destination PEs, which involves a little extra synchronization. And then once we have that, we can find the minimum time, do a reduction, and make everyone aware of what the GVT is. What's important about the GVT is once we know what it is, we know that it's impossible to roll back before this time, since it's the time of the earliest event in the entire system. And because of that, we can now commit events and reclaim the memory for those events that happened before the GVT. Okay, so the question here is basically, don't we need to also save the previous states of the LPs? And it turns out there are a couple different ways where you can handle optimistic simulations, one of which is just saving a history, like you suggested. How ROS actually does it is through reverse execution. So we have this history of events. If we execute them in reverse order, we can also get back to the state where we started at. So now that we know just a little bit of background on PDES, I'll talk about ROS. So ROS is a PDES engine developed at Rensselaer Polytechnic Institute in New York, written entirely MPI. It supports sequential, conservative, and optimistic modes, optimistic using reverse computation, as I just mentioned. It's highly scalable, and its peak performance, it achieved an event rate of 504 billion events per second on the full machine at Sequoia, so all 120 racks. This is compared to, in our current experiments, we've achieved 5.1 billion events on a single rack, so 120 times the resources gets approximately 100 times speed up, so it scales pretty well. These results were gotten using the p-hold benchmark. So p-hold is a common benchmark used to benchmark PDES applications. Essentially, what each LP in the p-hold benchmark does when it responds to an event, it just generates a new event with a random delay in time and then sends that event out to an LP chosen uniformly at random with the constraint that we have a parameter to say how many of the events will be sent remotely and how many will stay local. So the project itself is taking ROS, which is entirely written in MPI, and porting it over to Charm++. Why we want to do that? So obviously Charm++ has some nice capabilities. It's a fully asynchronous runtime system, which we want to leverage specifically when computing the GVT. With migratability, we can get load balancing, fault tolerance, checkpoint restart, stuff that would be much more difficult to implement in the MPI version. We also want to look at, in the future, fine-grained message aggregation. In PDES simulations, the events are generally very, very small, so sending these messages around is going to cause a lot of fine-grained communication. And then some of the other goals of the project, we want to maintain as close an API to the original ROS as we can, because it already has a bunch of users, a bunch of models written for ROS. So we want to allow model writers to use the new version of ROS with as little change as possible. And we also want to achieve similar performance to MPI ROS while adding these new capabilities. So I'll briefly talk about the design of the original ROS and what had to change in moving to Charm++. So in the MPI version of ROS, there are three key entities that manage their simulations. So you have your LPs, your KPs, and your PEs. LPs are what we expect from a PDES simulation. They have their behavior defined by the model writer. They execute events in timestamp order. And in the MPI version, they are mapped to what are called KPs, which are shown here in blue. So KPs are just a way to aggregate these very small grain LPs into a larger grain size. They store the previous events, so they keep track of the history for all of the LPs located on a single KP. And because of this, they control the rollback and the fossil collection. And finally, we have PEs. So PEs store the pending events that have come into the PE for the LPs that are located local to that PE, and it also controls and stores the data for computing the GVT. So moving forward into Charm, LPs, we ported over with no change whatsoever. The LP structs remain exactly the same, with the main difference being in how they're mapped. So now instead of being mapped to these KPs, which were just straight C structs of data, they're now mapped to migratable chars that the runtime system is aware of. These LP chars combine a lot of the functionality of the KP with some of the functionality of the PE from the original version of ROS. So mainly they hold the pending and the past event queues, as well as the LPs themselves. And the key benefit here is that now if we look at a single LP char, it not only contains a bunch of LPs, but all of the events that they will be executing in the future and all of the events they have executed in the past. So we can just take one of these chars, pick it up, move it off the core to a different core, and continue execution without a hitch. Finally, we have the PE manager, which has been elevated to the level of a group char. So again, it's now made aware to the runtime system is now aware of this PE manager. The PE manager is mainly in charge of managing the local chars, so the chars located on the same hardware as the PE manager, and it's in charge of controlling the overall scheduler, the control flow of the entire simulation, and the synchronization required for doing the GVT. So where we are so far with the port, we've completely ported over all three modes of operation, so sequential, conservative, and optimistic all work in the Charm++ version. They're deterministic and consistent with the original, so running a model in one versus the other, you'll get the same exact results every time. We've ported over three of the existing models, so we ported over p-hold to test performance, and we've also ported over PCS, which is a cell phone tower simulation, and Dragonfly, which is a network simulation for our Dragonfly network on a supercomputer. Particularly talking about the code itself, the MPI version of ROS had about 8.8 thousand source lines of code, whereas the Charm version got reduced down to about 4,000 lines of code. This reduction in complexity mainly came from the fact that we no longer had to handwrite a lot of complicated sending in MPI for figuring out where messages needed to go. Because again, in Charm, we have all the name management and the location management right there. And we've already started implementing some of the extra features I talked about and extra capabilities that Charm will give us. So now moving on to performance. Again, performance wasn't necessarily the key focus of this port. The key focus was to extend the capabilities of MPI ROS, but we did want to make sure that our performance was at least comparable to the MPI version. So these initial performance runs, again, were done with the p-hold benchmark on a single rack of Vesta, which is a BGQ machine up at Argonne National Labs, 64 threads or MPI ranks per node. And these initial runs didn't include any of the new features. So we wanted to get as close to an apples-to-apples comparison of the two versions of ROS as we could to see sort of where our shortcomings were and what we needed to improve upon. So here we have, on the y-axis here, we have the event rate in billions of events per second. So more events per second is better. And in the bottom here, we actually are exploring the space of the amount of communication we're doing in the p-hold benchmark. So on the left side here, we have just 10% of the events are sent remotely. The other 90% are local, all the way up to every single event being a remote event. So the first thing we notice is over here for like 10 and 20%, so a fairly low amount of actual communication. The MPI version is somewhat significantly better than the Charm version. But as soon as we hit around 30 and 40%, they're extremely close. And then actually starting at 40% and all the way up to 100%, the Charm version is actually faster than the MPI version, which was actually somewhat unexpected and nice to see. And we're currently looking into why, for example, when we're not sending that much, doing that much communication, why there's this performance discrepancy. It could be serial code we haven't optimized enough, or a particular configuration, but that's something we're currently looking into. So moving on to the new features that we've already added. So the following list of features have all been fully implemented and are currently being tuned and optimized. But the new features I'm going to talk about mainly fall into two camps. So there's the asynchrony in Charm++ that we use to enhance the GVT computation. And then there's the migratability and the benefits we get from that. So first, looking at the GVT computation, in ROS, how the GVT worked was each PE would execute some predetermined number of events and then hit a barrier or an MPI all reduce waiting to start the GVT. So this works perfectly fine if you have a balanced computation, but as we know, oftentimes things may end up unbalanced. So for example, here we have PE2 taking a much longer time to execute the same number of events as PE0, 1, and 3. And what that leads to in a situation like this is, well, PE0, 1, and 3 are all waiting to start the GVT. We end up wasting a lot of time with cores just sitting there not doing anything. So again, the GVT needs to be computed at somewhat regular intervals in order to both reclaim memory from events and it computes the minimum time in the system. So the minimum event that exists that we care about among all PEs. So the first thing we want to look at is how the GVT starts. And so in Charm++, broadcasts are done asynchronously. So the first simple change we could make is now as soon as a PE hits its set number of events, it can start the GVT by broadcasting to everyone else that we're ready to start. As soon as everyone else gets this message, they can quit what they're doing because all they're doing is executing more events. If they stop early, it's not going to affect correctness or anything, and then we can go ahead and start the GVT right away. The next factor we wanted to look at is once we're actually computing the GVT, is there any overhead we can reduce? So the scheduler in ROS is either executing events or computing a GVT. And in MPI ROS, it's exactly one of those things. So you notice here, we'll compute events for some amount of time, then we'll switch to computing the GVT, and all this time here is essentially a waste of time, because what we're doing when we're running these simulations is executing events. That's what we care about. That's what drives the simulation forward. So we want to see if in Charm++, in the Charm version, we can figure out how to reduce some of this wasted time. And we can do that, again, using the power of asynchrony. In Charm, all the reductions are asynchronous. So if we look at the three phases of the GVT, the first phase is quiescence detection. So that's where we actually have to wait to make sure that every single event has been received so we don't miss any events when we're computing the minimum time. Once we know the minimum time on each processor, we do the reduction to compute the global minimum time, and then we can do fossil collection, which is, again, reclaiming the memory and committing events. So in Charm, if we just take advantage of the fact that this reduction happens asynchronously, as soon as we get quiescence and we know that every event has been taken into account, we can start the reduction, and then while the reduction is happening, let the runtime system adaptively overlap the computation of more events with the communication for the reduction. And as soon as the reduction finishes, whenever that may be, we'll then do the fossil collection and reclaim our memory as normal. So this should reduce some of the overtime of the GVT. The last improvement is sort of the holy grail of GVT improvements, and that's we hope to eventually perfect the fully asynchronous GVT. So in this version of the GVT, we never stop executing events. So the current version we have implemented now takes a two-phase approach. So what we have here is events start executing in this case in the blue phase. At some point, we decide it's time to compute a GVT and reclaim some of our memory. So we switch computing events into the green phase, and then the GVT can use a library in Charm called completion detection, which is similar to the library for quiescence detection, just more focused. And now this completion detection engine sits here and waits for all of the events that were tagged as blue events to be received. As soon as we know we've received all of the events from this phase, we can then do a reduction to compute the minimum time based on these events, do fossil collection, all while we're executing events in the green phase. And then again, at some point in the future, we switch back to the blue phase of execution and let the GVT run in the green phase. So we're constantly executing events and letting the runtime system decide how to adaptively overlap the computation for the GVT and the computation for events. Finally, the last feature, of course, is migratability. So you saw we did, in designing the port itself, make sure that LPs were mapped to chars now rather than static, just standard passive C structs. And now that LPs are migratable, this enables load balancing, checkpoint restart, and fault tolerance. And all of this comes at minimal or no cost to the model writer themselves. The only extra work the model writer would have to do is, in certain cases, if the model's LPs have complex dynamic state that's allocated on the heap, the model writer would just be required to write a pupper to say how to serialize that extra state. Otherwise, for simpler models, they get this completely for free. So to wrap up, this is what we've done so far. These are all the features we have. I want to briefly mention where this work is going. So the first thing on our plate is definitely tuning and optimizing all these asynchronous features for the GVT. There's a lot of knobs we can turn, and how often to do the GVT, how many phases to have in the fully asynchronous version, and various different parameters that weren't existent in the MPI version. So we have a lot of work there to get those features up to snuff and sort of improving performance over the MPI version. The next point of research that might be the most particularly interesting topic to me is PDES-specific load balancing strategies. So currently we have a suite of load balancing strategies in Charm++ that all work with the PDES application now. But in PDES, inherently you have extra information that you can utilize when you have these load balancing strategies. For example, you have queues of upcoming events, so you know what work you're going to be doing in the near future. You also have the added information of what virtual timestamps these events are going to be executing at. So now not only can you balance load in the traditional sense, that you want to make sure that the computation and communication load is spread evenly across processors, you can also make sure that you spread the timestamps evenly along processors, therefore lowering, for example, the amount of rollbacks that you have to do and stuff like that. And finally, one thing we haven't implemented yet but have looked into is the topological routing and aggregation module. Again, I mentioned the events in PDES generally are very fine-grained, so we're going to end up with a lot of fine-grained communication. And this module is already built into Charm++ to sort of alleviate that and aggregate messages that are too small to perform well into larger sizes before sending them out. So we want to see if we can get benefits in ROS with this module as well. Any questions? Yes. Yeah, I don't think that's something that we've necessarily looked into yet, but it certainly seems like that's something, again, that with this extra information, with the load balancing and the migration, that could be something that we could optimize there by just making sure to arrange the chars with particular LPs in a way that would reduce that kind of problem. Mm-hmm. Mm-hmm. Yeah. Sure. So far, we've just used load balancing techniques to make sure that it doesn't affect the correctness, so we haven't looked too much at the performance of those yet. Although the persistence does depend on the model. For example, p-hold, there is absolutely no persistence whatsoever, but other models may have a little bit more persistence that we can still exploit in that sense.